Welcome to this class. So let's finally there is one final case that we have to look at. So SVM with the kernel function. Now so far we are assuming that the discriminant function is linear. Why should that be the case? For most of the data that we get, the discriminant function is not linear. What do we do with that is the question. Now the idea is very similar to what we did with the generalized linear regression. What did we do? You can convert a nonlinear decision boundary into a linear decision boundary by transforming data into some other space. That is exactly what we do here. Okay, so let us look at it. Uh, so define a function phi that is from Rd to Rd dash. So typically d dash is much greater than d. Now what is not linearly separable in the data domain X, okay, will sometimes become linearly separable in the transform domain. Example can be, you take the Fourier series itself. Fourier series, right, it's linear in the exponential domain, it's not linear in X or whatever the t, whatever your variable is, but it's linear in the exponential domain. So we are not guaranteeing that the data will become linearly separable after you transform, but we have a formulation to handle the case where the data is not linearly separable as well. We just need the slack formulation. However, transforming data and projecting it onto a higher dimensional space, okay, uh, will make the linear separability more plausible. Okay, that is why you choose a phi, okay, such that the data is taken from a domain D to D, I mean RD to RD dash, where D dash is much higher than D. Okay. Now with this, the dual function to be solved will be, so we will have half, what was that, it is, yeah, mu I. So maximize over mu I minus half some over I some over j mu I mu j yi yj. Now we will not have xi transpose xj, we will have phi of xi transpose phi of xj, correct. So this will be the problem that we will be solving. Does it make sense? Okay. So far so good. So now we still have to answer this question, right? How do we choose this phi in practice? Remember I told you that this phi is a user defined choice, you know, you choose it. We'll get to that in a while, but what is to be noted is that the problem that we will be solving will now have phi I transpose phi of xi transpose phi of xj instead of xi transpose xj, because we have transformed the data into some other space. Now suppose, of course, I mean there is this constraint that mu has to be between 0 and c, because we are solving the slacked version of this problem. Suppose there exists a function, there is a function function k, okay, this function k takes operates on the cross product of Rd and Rd and maps it to real numbers, in fact positive real numbers, such that compute that kernel on 2 data points, it will give you this for all I in j. What does this mean? Let us say that there exists a function k, okay, and this k is what is called as the kernel function. So what this will do is, it will take given 2 data points xi and xj, if you pass this if you pass these 2 data points to the kernel function, it will compute the inner product, okay, of these 2 data points in the projected space. Suppose a function like this exists, okay. So what happens to the problem that we will be solving in this case? Now instead of the SVM problem, SVM dual problem will be, now we will have mu I minus half mu I mu j yi yj xi comma xj, right. Here there were inner products between the projected data points. Now if this is equal to a function kernel, then it will be equal to this. Now what does this mean? Is it okay? Is it clear to all of you what we are saying? This means that if we can find a kernel for a given projection, then we do not even have to know what the projection is, as long as we can compute the kernel. Good question. The question is, if we do not know what the projection is, how do we know that it is linearly separable? There is no guarantee to that. However, I will show you that there are cases where this phi can be a projection to an infinite dimensional space, while the kernel can be computable in the data space. So you project your data onto an infinite dimensional space, okay, there you assume it to be linearly separable, and you don't actually project the data, you only compute the kernel. We will see that. But what is to be noted right now is that if there exists a function like this which will operate in the data domain, okay, and computes the inner product, which is called the kernel, then to solve the SVM problem, max margin classifier problem, you do not even have to know what the projection is, as long as the kernel can be computed. That is okay, no, that is fine, okay. Hold on, huh? Yeah, question, yeah. Had, I was just thinking about it, has it to be, inner products are bounded between -1 and 1, right? No, it is cos theta, right? It can be between -1 and 1. Yeah, so it means, see, I can be, it is very safe to say R, yeah. However, let's come back to this in a while, we will have to talk about something called Mercer's theorem. So, that says that suppose, so k bar is an n by n matrix with the ijth element being equal to k of xi comma xj, where k is a kernel function. Okay. Now, if k bar is positive semi definite for every data set D, then k function k is a valid kernel. So, what do you mean by a valid kernel? A valid kernel is one, okay, one that corresponds to a projection phi. So, what this theorem is saying as follows: suppose you construct a kernel function, okay, and you take a data set and compute the kernel for all pairs, you get a matrix. If that matrix is positive semi definite, then that kernel function has to correspond to a projection. You understand? This means that we do not have to look at a transformation and then ask what kernel gives the inner product for this transformation. We can do the other way around. What we can do is come up with some kernel function and see if the kernel matrix for that particular kernel function on every data set is positive semi definite. If that happens, then we can be guaranteed that this kernel function corresponds to some projection of data. That is how people do it, in the sense that they come up with novel kernel functions, not with novel transformations, because every kernel function, as long as it is a valid kernel, okay, it corresponds to a transformation of data. That is what Mercer theorem says. Okay, yeah.
Is it give a way to find the project, like the projection from kernel function?
Not all kernel, you will not know what the projections are for every kernel functions. In fact, we will see an examples where the projection for a particular kernel function is to an infinite data space. There is something called a Gaussian kernel. The projection for that corresponds to an infinite data dimensional projection.
But there can be an infinite basis by which you can describe it.
Of course, but why do you want to know that? See, ultimately you want to find a max margin classifier and you assume that your data is linearly separable. And if you project your data onto an infinite dimensional space, then linear separability is a fair assumption to make. Okay, and you anyway have the slack there. Now use a kernel that corresponds to infinite projection to an infinite data dimensional space and ensure that this kernel is valid through Mercer's theorem. Then solve SVM, that is all you need, no? That is exactly what is done actually, right? So let us look at examples for some valid kernels. So, please note that never in our treatment we said that projection will ensure or guarantee linear separability. It's not, there is no theorem that says that once you project your data onto a space it becomes linearly separable. There is no guarantee there. Yeah. So this is something called polynomial kernel. You take two data points x1 x2 and the kernel is 1 plus x1 transpose x2. This is a scalar, raise it to power p. This is the polynomial kernel. And there is Gaussian kernel. Let me write sigmoid kernel. You take data points xi, x1, x2 and this is equal to tan h a x1 transpose x2 plus b. an interesting thing is, suppose this is your kernel, okay, what would be your final W star with a kernelized version? W star will be mu I star plus mu I stars times yi times phi of xi, right? Now how do you compute that now? You do not know phi. You want your W star. Exactly, right? You do not want W star. The final classifier is W transpose X. W transpose X. W transpose X is phi I transpose phi X. That will be kernel. You understand that? Yeah. So you do not need phi for anything. The final classifier will be W transpose X. While W has phi of X, the W transpose X will have inner products which will be kernel. Okay. Now if that kernel, okay, let us look at that. So final classifier discriminant function g of x will be W transpose x or phi of x. That will be W transpose phi of x, and this W transpose is some more support vectors mu I star yi times phi of xi, okay, this times phi of x, right. This will be phi of xi transpose, you have phi of x, that is tan h axi transpose x plus b. See, this is a single hidden layer neural network, as we will see later. Anyway, so that's, you can ignore that comment because you don't know what a neural network yet is, but yeah, so this is what it is. Okay, linear function of data, sigmoid, and then some scaling and a sum, which is a neural network. Anyway, so the point that I wanted to make is, even to take a final decision which is compute the discriminant function, you don't need the transformation, all you need is a kernel, right. So this is the sigmoid kernel. Another kernel that is used in typically in practice is what is called as the Gaussian kernel, and Gaussian kernel is the one that corresponds to infinite projection of data onto infinite data dimension space. Gaussian kernel kg, if you take x1 comma x2, it's given by e power norm of x1 minus x2 squared by sigma squared, and the final discriminant function will be very similar to a neural network with what is called as an RBF kernel, right? But anyway, so that's a side point. Now this Gaussian kernel corresponds to projection of data onto infinite dimensional space. Okay. Now Gaussian kernel is a standard kernel that is used for SVMs, because we know that projecting data onto an infinite dimensional space, that is where you can hope it to be linearly separable. So a standard choice for SVM is the slack formulation with a Gaussian kernel. Now you have two hyperparameters, right, C and sigma, and that is why when you run libraries, standard libraries such as libsvm, it takes data as one of the parameters. That function call will take data as one parameter, the other two parameters are C and sigma. People typically do a grid search over C and sigma. Okay. Right. This is about max margin classifiers and SVM. Finally, what you actually do is assume the slack formulation and take any kernel, typically Gaussian kernel is taken, and then do a grid search over the parameters and solve the dual problem using standard solvers to get your mu and mu star and then the corresponding discriminant function. Okay. Now there is one little piece that I have to do before we complete this discussion, which I will take 10 minutes and complete it. So we will look at SVM from an ERM lens. Just a second. As regularized ERM. Yes.
The same Gaussian kernel will be used in Parson window.
Huh, correct. See there, strictly speaking, phi is not the kernel, k is the kernel. That is why remember when I introduced Gaussian, Parson window, I was a little hesitant to call that phi as kernel, because kernel is the one that computes the inner product between the transformation. So that phi in Parson window is simply a transformation of data. Even in generalized linear regression, some people refer to this phi as kernel. Okay, but yeah, the kernel typically refers to this for particular function. I mean, yes, now that you reminded me of that, see this trick, okay, where you compute inner products in a projected space, okay, using a function that is defined on the pre-projected space, data space, is called kernel trick, and it is used very widely in machine learning. Okay, so wherever you get a formulation where there is some projection and everything, if you can formulate everything in terms of inner products in the projected space, then you can do all of it using kernels. So there is kernelized max margin classifiers, there is kernelized neural networks. You can think of kernelized, in fact there is something called kernelized nearest neighbor, because even nearest neighbor needs you to compute this inner products. Now if you can replace this inner product with a kernel, then it becomes kernelized neural networks, I mean nearest neighbors. So this is called the kernel trick, where the trick is that even without getting onto the projected space, you can do everything that needs to be done by computing the kernel in the. So if you can formulate your entire problem in terms of inner product in the projected space, then you can do everything using kernelized trick. So that's called the kernel trick. Okay, fine. So let's look complete that final piece. So we have SVM which Slack formulated this way: W transpose W plus C times subject to yi times W transpose xi plus b is greater than or equal to 1 minus xi. So this is the Slack formulation, correct? Now let's observe this: given any W and b, xi has to satisfy this particular constraint. It has to be greater than or equal to the max of 0 comma 1 minus yi W transpose xi plus b. Why is this the case? Now I just rearrange these terms, okay, bring the xi to left and the other term to right. So which means that xi is greater than 1 minus this particular term. It can also be 0 when, yeah, xi can, if it's correctly classified, that can also be 0. So it has to be either this term or 0. So it has to be maximum of those two terms. For any w and b, xi has to satisfy this, correct? Now with if I now I can rewrite the optimization problem as follows now. So I can, why did I do this? I did it because I wanted to combine both these constraints, okay, into one and write the Lagrangian for this problem. That's it. So if I do that, it's a minimization over w and b. We have half w transpose w plus c times, instead of xi I can write this, correct? This is the problem. Now what does this look like? Now this is a loss function plus a regularizer on W, isn't it? And what is the loss function here? The loss function that we are looking at correct. This is the loss function, and this loss function is called hinge loss. Now the punchline is that SVM with a slack is regularized empirical risk minimization with hinge loss and an L2 regularizer on your parameters. And the decision boundary that we are looking at are linear discriminant functions. Of course, generalized linear discriminant functions, because you also have the projection of data onto some space, that is it. Now, if I were to write this loss function and then solve it, right, instead of doing that, we approach the problem from a different end, right. We assume that it is a linear discriminant function and we wanted to maximize the margin and we got onto a solution, but if you start from this, you will exactly go to the exact same solution that SVM gives you. So remember the moral of the story, right. Modify the loss function, modify the regularizer, your algorithm changes. So everything that we do in machine learning is modifying loss functions, modifying the hypothesis class and adding a regularizer. That is it, right. You can do it in 100 ways. So this is one way where we assumed it to be something, and we put the constraint, or we assume the discriminant function to be linear and we put the constraint that the margin has to be maximized. Okay. What we are effectively doing is choosing a particular type of loss function and putting a regularizer and then optimizing for it. Same thing happens with neural networks, same thing happens with decision boundaries, transformers, everything, right. So that is why I told you, because regularized empirical risk minimization is the heart of machine learning, I do it exactly at the midpoint of the course. Right? Everything that we do is that in different ways, which is also a Bayesian way of looking at world. Okay. Right. So this will see, again, as I said, SVMs are not the go-to choice of classifiers in today's world. However, we studied this because you look at how to formulate problems from first principles. And also I just mentioned that with this the most powerful result about SVM is that with this formulation one can show that the true risk with this uh, can be bounded with the empirical risk and the number of data points, okay, which also depends on the margin, distance of the margin. So the higher inversely to distance of the margin, so the larger the margin is, the better the generalization capabilities. So then I think machine learning should be solved, no. If we can do this, then what is left in ML? The problem is that for very high dimensional data, right, the assumption that the data is linearly separable with a projection fails. In fact, 20 years before, not 20, late 90s, 35 years before, SVM was the state of the art. Historically speaking, neural networks came much before SVMs, right. But SVMs were state of the art because you could provably give an algorithm that would generalize. But at the scale of data, okay, that started coming out in early 2000s, etc., these kernel functions did not generalize because there is no guarantee that the data is linearly separable even after you project them. Okay. Okay, so this completes max margin classifiers. From now on, from the next class, we will start with we'll go to neural networks, okay, which are the choices of classifiers that are currently used for most of the applications. We'll look at this backpropagation algorithm and a few architectures, and then we'll move on to what are these things? Decision bound classification regression trees, right? Random forests and we were before ensemble methods. What is this? Decision trees, classification regression trees, they are called cards. Okay, thank you. That's it.